Hello everyone, today I'm going to present you our paper, Analysis of two equivalent circuit models for the state of charge estimation using Kalman filters. The structure of this presentation is the following. First, I'm going to present you the importance and challenges of agricultural robots. Then, I will explain the importance of the battery state of charge estimation and the challenges related to an accurate estimation. After that, I will show you two equivalent circuit models and several parameter estimation methods. Then I will present the result of the state of charge estimation implementation, and finally I will share with you the conclusions of this work. Agricultural robots can be used to increase the productivity of farms. The implementation of robots in farms has several benefits like improving precision farming, producing more food, replacing the use of fossil fuels, reducing soil damage due to high machinery, and reducing the use of pesticides. However, agricultural robots face some challenges that must be overcome to increase the presence of robots on farms. Improving some aspects of the battery is needed, like reducing battery charging time, increasing the operation time, and implementing efficient energy management strategies. The battery must provide sufficient power to avoid unexpected shutdown, because manual pickup of robots is not an easy task, due to robots' weight and complex environment that farms represent. Also, we want to avoid over-discharge and overcharge because we don't want to reduce the battery lifetime. An overcharge situation or a bad battery management could lead to a fire that could be terrible for crops. The battery state of charge is a critical information to solve the problem related to energy management of the robot. The state of charge provides information about the remaining energy in the battery and is a critical parameter to ensure safe and efficient operation of the robot. State of charge is essential to design on the operation of agricultural robots and could help to increase operation time and lifetime, avoid over-discharge and unexpected shutdown due to battery depletion, and also avoid battery damage due to overcharge that could lead to a fire or an electrolyte leakage. Unfortunately, the battery state of charge cannot be measured and must be estimated. The state of charge estimation is not an easy task. Several methods for state of charge estimation have been presented in the literature. However, improving the accuracy of this method is still a significant challenge. Among the traditional methods, we can find the open circuit voltage methods and the Coulomb counting methods. However, both methods are unsuitable for mobile robotic applications due to their limitations. Recently, several state of charge estimation techniques based on artificial intelligence have been presented. However, the significant amount of data needed to perform an accurate state of charge estimation make these approaches impractical. Several approaches based on equivalent circuit model has been presented recently in the literature. Equivalent circuit models consist of a electrical circuit containing several resistors, capacitors, and sources that models the battery's behavior. Using this model in combination with a state observer like the Kalman filter, we can estimate the state of charge of the battery. Now I'm going to present you the process of battery modeling and parameter estimation using two equivalent circuit models. Model-based methods could overcome the limitations of the conventional approaches. Self-charge estimation could be performed based on battery equivalent circuit model that represents the behavior of the battery using the state equation of an electrical circuit. Although an accurate battery model is important to improve the accuracy of the state of charge estimation, it is important to keep the model as simple as possible to be implemented in embedded systems suitable for agricultural robots. This research aims to compare two circuits models, the RC model and the 2RC technique model, in order to identify the advantages and limitations of each one. The result of this research will be used to determine which model is more suitable for battery state of charge estimation. The first model to analyze is the RC model. It consists of two RC branches and a terminal resistance that model the voltage drop when a battery is connected. In this model, the bulk capacitor is used to model the battery's storage capacity, and the surface capacitor is used to model the battery's surface and diffusion effects. Looking at the equation of this model, we can see that the battery is modeled using linear equations. Then, a linear state observer can be used, like the Kalman filter. The battery open circuit voltage was found by estimating the voltage across across the bulk capacitor using a linear Kalman filter. Then, the state of charge can be estimated by using the open circuit voltage versus state of charge curve. The IRE pulse power characterization test dataset provided by University of Wisconsin-Madison was used to estimate the parameters of the RC model and also to validate the performance of the state of charge estimation methods. This slide shows the value of the parameter of the equivalent circuit model. With the HPPC test, we have obtained the values of the battery open circuit voltage versus the state of charge curve and the circuit's parameter, bulk capacitor, bulk resistance, surface capacitor, surface resistance, and terminal resistance. We can see that the bulk capacitor has a bit value since it models the battery's energy storage capacity. Since the parameters of the model have been estimated offline and do not change with the battery state of charge, the performance of the model is affected, and there you can see there is an offset between the measured voltage and the model voltage. To improve the accuracy of the battery model, the recursive least square method was implemented. To implement the recursive least squared for parameter estimation, the transfer function of the model is used to define the regressive vector of the battery, and then we can obtain the parameter online. This method can update the parameter of the equivalent circuit model online. Then we can consider several factors that affect the battery, like aging and capacity fade. Also, there is no need to perform the long HPPC test, reducing the testing time and the manual work to estimate the parameters online. After implementing the recursive least square using Simulink, we can see that the performance of the model has improved. The error is reduced when the parameters are estimated online. The 2RC model consists of two RC networks to model the battery diffusion effects and a terminal resistance to model the voltage drop when a load is connected. Looking at the equation of this model, we can see that this model is non-linear because the output voltage is affected by the battery open circuit voltage that is a function of the state of charge. Then we used a nonlinear state observer, the uncentered Kalman filter, to estimate the state of charge. Each pole of the HPPC test is analyzed individually and represents a state of charge level. A set of parameters can be set for each state of charge level. Since we have 68 pulses, we can have the parameters for up to 68 state of charge levels. The initial parameters obtained by curve fitting were used as a preliminary version of the final model parameters. Using Simulink design optimization to analyze each pulse, the initially estimated parameters can be refined. The reason to make an initial estimation is to avoid local minima and facilitate the optimization of the parameter when using the Simulink design optimization tool. In this slide, we compare the performance of the result of the parameter estimation of the 2RC70 model with the previous model. We can see how an offline estimation that depends on the state of charge levels can reduce the error of the model. Also, we can see how online parameter estimation has the better performance. The state of charge estimation was implemented using Kalman filters. Recently, several articles have shown promising results using equivalent circuit models in combination with Kalman filters. Using the bulk capacitor voltage as the battery open circuit voltage has provided good performance at high state of charge levels. However, the state of charge estimation performance at lower state of charge level is not good. Also, we compare the same model using different values of measurement error covariance R, and we can observe how a bad initialization of the filter parameters can affect the accuracy of the battery state of charge estimation. This slide shows the result of the state of charge estimation using the RC model in combination with the online parameter estimation method. The estimation is heavily affected since the parameters are changing constantly. We should consider using the extended or uncentered Kalman filter, which are adapted for nonlinear Kalman filters, in order to improve the performance of this state of charge estimation. This slide compares the performance of the three state of charge estimation methods analyzed in our study. We can observe that the state of charge estimation using the 2RC70 model offers the best performance among the other two methods. In this slide, we can analyze the result of the 2RC model. It's important to notice that the number of parameters affect the state of charge estimation. This slide shows the model performance using 11 state of charge level and 68 state of charge level respectively. We can see that with a reduction of the parameter, the accuracy of the state of charge estimation is reduced. However, it's important to note that the filter's initial state and parameters were not modified. Then we could expect a good state of charge estimation if we tune the uncentered Kalman filter initial parameter to each model. It is important to find a good trade-off between the number of parameters and the precision of the state of charge estimation. This paper presented a study of two equivalent circuit models used for a state of charge estimation. We can see that as I mentioned before, the 2RC model had the better performance. However, the RC model using the parameter estimated offline in combination with the Kalman filter show a good performance and is easier to implement than the state of charge estimation with the 2RC model. Then we could consider using this one for agricultural robot applications. Online parameter estimation technique improve the model performance while reducing the number of tests needed to build the model. However, for agricultural robot application, special attention should be given to the complexity of the parameters process because new techniques should be implemented in embedded system. Therefore, future work on battery modeling should focus on estimating the parameters online while keeping the parameter estimation process simple. Several tests must be performed using agricultural robots in farms to validate the performance of this method. Although some methods have shown good performance under simulations and laboratory environments, validation under actual farm conditions is needed to confirm the effectiveness and accuracy of the state-of-charge technique. These are the results of my study that I wanted to share with you. Thank you very much for your attention.